this episode, we're going to take a topic that often gets presented as pure math and turn it into a practical way to describe patterns hiding inside a dataset. When people hear eigenvalues and decompositions, they often assume they are being asked to do advanced calculations by hand. But for the CompTIA Data AI exam, the real skill is understanding what these ideas mean and why they matter. At a high level, eigenvalues and decompositions help you answer questions like where does the variation in my data live, which directions capture the most structure, and how can I simplify a complex dataset without throwing away the most important signal. This matters in data AI because real datasets often have many features that overlap in what they represent, and that overlap can make models harder to interpret and harder to train reliably. Decompositions give you a way to rotate your view of the data so that the most meaningful directions become clear and the noise becomes easier to identify. By the end, you should be able to explain what an eigenvalue represents in everyday language, what a decomposition is doing conceptually, and why variance and structure are connected in a way that supports practical modeling decisions. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good place to begin is with the idea that data has directions, not just values, especially when you think of each item as a vector in a feature space. If you have many points in a multidimensional space, those points might spread out more in some directions than in others. For example, if two features tend to rise together, your points might form an elongated cloud along a diagonal direction, indicating a dominant pattern. If features vary independently, the cloud might spread more evenly. This is why variance is not just a single number. It can depend on direction in the space. When you talk about variance in one feature, you are looking along one axis, but the most informative axis might be a combination of features, like a diagonal that captures a shared trend. Decomposition methods, especially those related to eigenvalues, help you discover those informative directions automatically. Beginners often assume you should always analyze features one at a time, but important structure often lives in combinations. Understanding that structure is the first step to understanding why eigenvalues matter. To connect this to something more concrete, think about what happens when features overlap in what they measure. If two features both reflect roughly the same underlying phenomenon, like two sensors tracking the same behavior with different noise, then those features will be correlated and the data will have redundant information. Redundancy means you can describe much of the dataset with fewer independent directions than the number of raw features suggests. That is useful because models often struggle when they must learn from many redundant signals, and interpretation becomes messy because multiple features appear important for the same reason. Decompositions can reveal that redundancy by identifying a smaller set of directions that explain most of the variance. Beginners sometimes think reducing dimensions is only for making things faster, but it is also about clarifying what the data is really doing. If you can represent the dataset in a basis that separates major patterns from minor noise, you can train models more stably and interpret relationships with less confusion. The exam often tests this high-level motivation. Decompositions are about structure, not about abstract math for its own sake. Eigenvalues show up when you analyze how a transformation stretches or compresses space along certain special directions. A transformation can be thought of as a rule that takes vectors and turns them into other vectors, which is exactly what many matrix operations do. An eigenvector is a direction that remains a direction after the transformation, meaning the transformation might scale it, but does not rotate it into a different direction. The eigenvalue associated with that eigenvector is the scaling factor, telling you how much the transformation stretches or shrinks vectors in that direction. For variance and structure, the transformation you often care about is tied to how data varies, such as a covariance matrix-like representation that describes relationships among features. In that context, eigenvectors represent directions in feature space that capture independent patterns of variation, and eigenvalues tell you how strong each pattern is. A large eigenvalue means there is a lot of variance along that direction, while a small eigenvalue means there is little variance along that direction. Beginners sometimes hear eigenvalue and think it is a random score, but in this setting it is a measure of how much the dataset spreads along a particular structural direction. This is why eigenvalues are so closely connected to understanding variance. A decomposition is essentially a way to break a matrix or a dataset into simpler pieces that reveal structure. Instead of treating the dataset as one big tangle of numbers, you express it as a combination of components that each have a clear role. The most common idea beginners encounter is that you can represent data in a new coordinate system where axes are chosen to align with the directions of greatest variance. This is often associated with principal component analysis, PCA, which is a method that finds those directions and orders them by importance. The decomposition gives you a set of orthogonal directions, meaning directions that are independent in a geometric sense, so each direction captures a distinct pattern not captured by the others. The eigenvalues then tell you how much variance each direction explains. If the first few eigenvalues are much larger than the rest, it suggests the data has low effective dimensionality, meaning most structure can be captured in a small number of components. Beginners often assume high-dimensional data must require high-dimensional reasoning, but decompositions often show that the meaningful variation lives in a smaller subspace. That is an encouraging insight because it means complexity can be reduced without losing the main signal. Variance is central here, but it is important to interpret variance correctly rather than treating it as an automatic proxy for importance. Variance measures spread, and spread can come from meaningful differences, but it can also come from noise, measurement instability, or changes in scaling. A feature that is measured in large units can have high variance simply because of its scale, not because it is more informative. That is why standardization and normalization often appear alongside decomposition concepts, because you want variance to reflect meaningful variation rather than arbitrary units. Beginners sometimes see variance explained and assume the first component must correspond to the most meaningful real-world factor, but that is not always true. The first component is the direction of maximum variance, and if some irrelevant factor dominates variation, the first component can capture that irrelevant factor. Exam questions might test whether you understand that variance explained is about data spread, not about causal importance. A mature interpretation is that high variance directions capture dominant patterns, but you still need to check whether those patterns align with the task. Decompositions reveal structure, but they do not automatically label what that structure means. One of the practical uses of eigenvalues in this context is deciding how many components to keep when you simplify data. If you keep only a few components, you compress the dataset, which can reduce noise and redundancy, but you also risk losing information that matters for prediction. The eigenvalues provide a natural ranking of components, so you can retain the directions with the most variance and discard those with very little variance. This is often justified because very small eigenvalues correspond to directions where the data barely changes, which might be dominated by noise or might represent minor variations that do not carry much signal. Beginners sometimes think discarding components is always safe as long as you keep a large percentage of variance, but the truth depends on the task. A small variance direction can still be important if it is strongly predictive of the label, especially in classification problems where subtle patterns matter. So the eigenvalue ranking is a useful guide, not a guarantee. On exams, you may be asked why keeping top components can help, and the correct reasoning often involves reducing dimensionality, removing redundancy, and focusing on dominant structure, while acknowledging that some information may be lost. Decompositions also help you understand collinearity, which is the situation where predictors overlap heavily and make regression-like models unstable or hard to interpret. When features are highly correlated, the dataset has directions with strong variance and directions with almost no variance, because the correlated features move together. The low variance directions correspond to tiny differences between the correlated features, which can be sensitive to noise. In a regression model, trying to estimate separate effects for highly correlated features can lead to unstable coefficient estimates, because the model cannot confidently assign credit to one feature versus the other. Decomposition thinking reveals this as a geometric problem. The data cloud is thin in certain directions, meaning there is little independent information there. Small eigenvalues can signal these thin directions, which is one reason eigenvalues can be associated with diagnosing ill-conditioned problems. You do not need to compute condition numbers for the exam, but you should grasp the idea that redundancy creates unstable directions and decompositions expose that. This connects directly to why simplifying or rotating the feature space can improve model stability and interpretability. When you can explain that correlated features create redundancy and decompositions isolate the independent patterns, you are demonstrating practical understanding. Another way decompositions help is by providing a compact representation that can reduce noise sensitivity. If your data includes many weak features that mostly contain noise, those features can clutter the space and make distance comparisons or model fitting less reliable. By capturing the main patterns in a smaller number of components, you can sometimes improve generalization because the model focuses on stable structure rather than overfitting to random variation. This is not automatic, and it depends on how well variance aligns with signal, but it is a common motivation. Beginners often assume more features always help, but more features can also mean more ways to fit noise. Decomposition acts like a filter that keeps the strongest shared patterns and compresses away small, scattered variations. The exam may present a scenario where dimensionality reduction helps combat overfitting or improves performance on new data, and decomposition-based reasoning is often the explanation. The key is to speak about the trade-off. You gain simplicity and noise reduction, but you may lose subtle information. Thinking in terms of stable structure versus fragile noise helps you frame that trade-off in a mature way. It is also important to understand that decompositions create new features that are combinations of original features, which can change interpretability. The new components are often linear combinations, meaning each component mixes multiple original variables with different weights. This can make the representation powerful, but it can also make it harder to explain in everyday terms because the component is not a single original measurement. Beginners sometimes assume decompositions always improve interpretability because they reduce dimensions, but interpretability depends on what you mean by interpretability. A smaller number of components can make the model simpler, but each component can be harder to describe. In some contexts, you accept this trade-off because prediction quality and stability matter more than feature-level explanations. In other contexts, you might prefer models built from original features because they map more directly to human understandable concepts. Exam questions might test whether you understand that decompositions can reduce dimensionality at the cost of feature-level interpretability. The responsible stance is that decompositions are tools, and choosing them depends on whether your priority is performance, stability, or explanation. You should also connect decompositions to the idea of compressing information in a way that is grounded in data structure, not in arbitrary selection. When you choose a subset of original features, you are keeping some raw axes and discarding others, which can throw away shared patterns that are spread across many features. Decomposition-based approaches instead create axes aligned with how the data actually varies, which can capture shared trends more efficiently. This is why decompositions can sometimes outperform naive feature selection as a compression method. The eigenvalues give you a quantitative view of how much each axis contributes to explaining variation. If the eigenvalues drop off sharply, you have evidence that a small number of components may capture most of the dataset structure. If the eigenvalues decline slowly, it suggests the data has more distributed variation, and aggressive compression may lose important information. Even without drawing a plot, you can reason about this by imagining whether your dataset has a few dominant patterns or many small ones. The exam may describe a dataset where a small number of factors drive most variation, and decomposition thinking fits that story. Your job is to connect the words of the scenario to the idea of variance concentrated in a few directions. Another beginner misunderstanding is to treat eigenvalues and decompositions as only relevant to one method, but the underlying ideas apply across many tools. Anytime you want to understand how data varies, you can benefit from thinking in terms of directions of spread and independent patterns. Anytime you want to reduce redundancy, you can benefit from expressing the dataset in a basis where correlations are separated. Anytime you want to stabilize a model that is sensitive to collinearity or noise, you can benefit from focusing on dominant structure. Decompositions are a family of methods, and while the exam may name certain ones, the deeper reasoning is about structure extraction. When you see words like variance explained, principal directions, component weights, or dimensionality reduction, you should recognize the same core story. The data cloud has shape, the decomposition describes that shape, and eigenvalues quantify the strength of each shape direction. This coherent narrative makes it easier to answer questions without getting lost in method names. To close, eigenvalues and decompositions give you a geometric way to understand variance and structure that is extremely useful in data AI reasoning, even when you never compute them by hand. You learn that data spreads more in some directions than in others, and those directions can be combinations of features rather than single feature axes. You learn that eigenvectors represent special directions tied to a transformation of the space, and eigenvalues represent how strongly the data stretches or varies along those directions, which is why they measure pattern strength in variance-focused decompositions. You learn that decompositions can reveal redundancy, reduce dimensionality, and improve stability by focusing on the strongest shared patterns, while also bringing trade-offs in potential information loss and reduced feature-level interpretability. You learn that variance explained is a measure of spread, not automatically a measure of causal importance, so you must connect decomposition outputs to the task context. Most importantly, you build a way to talk about these topics as structure discovery rather than as math intimidation. When you can describe a decomposition as rotating the data to line up with its strongest patterns and using eigenvalues as a ranking of how much those patterns matter, you are ready to interpret exam questions about variance, redundancy, and dimensionality with confidence and maturity.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.